Alright, so in orbital notation, we are going to continue using the off-ball principle. We're going to continue following the arrows, but this time we are going to draw boxes to represent each orbital. So first of all, we need to think about those letters again. Alright. An S, so quantum number L, if it has an S on it, 1s, 2s, 3s, how many electrons can it hold? 2. Alright. A P holds how many? Good. A D holds how many? Okay. An F holds how many? 14. Alright. What do you notice about those numbers? They're all even. That is correct. Alright, so in orbital notation, we're going to follow the off-ball rule, but we're going to show the actual electrons. So for an s orbital, we draw one box. That one box can hold 2 electrons. Okay. How many boxes do you think we're going to draw for the p orbital? 3 boxes, right? And that's a terrible box. But usually the boxes are connected when we draw orbital notation. How many boxes do you need for a d orbital? 5, that's correct. Yep. How many boxes do you need for an f orbital? 7, that's right. Alright, so this is a little bit more tedious, but it does show us a couple of things. Okay, so let's just do carbon, and I'll do an example, and then we'll point out a couple of important parts. So carbon has how many electrons? We go back to our periodic table, we look and see carbon has an atomic number of 6. So in its ground state, in its normal existence, not an ion, it has 6 electrons as well. So I'm going to write that out here. Okay. If I write its electron configuration, I'm going to refer back to off-ball principle. Okay. I'm going to write 1s2, there's 2 electrons, 2s2, there's 4 electrons. What comes next? 2p, but do I need all 6 of them? Nope. I need, let's see, 1, 2, 3, 4. I just need 2. Okay. So, that is electron configuration. If I'm going to do orbital notation, then I'm going to come up and look at what we just talked about for boxes. So S holds 2, I need 1 box. A lot of times they will write what it is at the bottom of the box. Just wrote on my hand. And we see that that 1s orbital is full, so it has 2 electrons in it. We go up and we go down. Let's make that closer so you can see a little better. Okay, so for the 2s, how many boxes do I need to draw for 2s? Just 1 box, right? And then we label it under the bottom. And how many electrons are in the 2s? 2. So it's full. We go up and we go down. So then for a P, how many boxes? We need 3 boxes for P. But this time we only have 2 electrons. So we're going to label it 2P. And those electrons are going to fill 1 in each box until we have to double up. It's kind of like rooms in a house. If there's enough rooms for you to have your own room, you're probably going to have your own room. But when there's too many people, that's when you have to double up, right? So that's the same idea that we have here. Give me a thumbs up if that makes sense. You got it. Okay, pretty clear and straightforward. Now we're going to put a couple of names with that. Yes, sir?
So the 2P, yes, we usually have 3 boxes.
Mm-hmm.
Would it have 3 ups and 3 downs?
You would, yeah. So if we did a bigger element, let's say we did fluorine. Let's go ahead and do an example for fluorine and we'll add to that because that's a great question and it does lead right into where we're going. It has 9 electrons. So the electron configuration is 1s2, 2s2, 2p5, right? But the orbital notation is going to look like 1 box, and we have an up and a down. Another box, and we have an up and a down. And then we have the 3 boxes. And in this case, we would go up, 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 and then backfill with down, down. All right, and so let's put some names and some concepts on what we're looking at, because it seemed like most people had thumbs up that this drawing boxes thing makes sense. And that is called orbital notation. Okay, so there will be times when you have to pick out the orbital notation on the test next week, and you're going to have to remember, oh yeah, the boxes are the orbital notation. Okay. So let me get some colors so that we can see a little bit more clearly. Okay. We're going to kind of circle the arrows and pull that out first. The arrows equal the spin of the electrons. So that question that you had earlier in your bell ringer, which if one electron is spinning clockwise, the other one would spin counterclockwise. We show that with an up and a down arrow because in the world of atoms, left and right and clockwise and counterclockwise and up and down are kind of irrelevant. So we have to show some way that they're going the opposite direction. Does that make sense? Okay, so we just use up and down to show, and we'll go ahead and write that too. Electrons spin in the opposite direction if in the same. You could use box or orbital because each of these boxes is like a section, a subsection of this orbital. Okay. Okay, so this concept, does this make sense? Thumbs up if this makes sense. All right, let's put a name on it. This is called Pauli's exclusion principle. Pauli's exclusion principle. So if you remember the conversation we had about quantum numbers a few days ago, this spin is one of those quantum numbers. The spin is m sub s. Okay. So if we look at the electrons, now this is one of those theoretical kinds of things. Like, we as normal humans or even normal chemists are not going to look at a single electron in a single atom. It's sort of for conceptual purposes. So this electron has an up spin, which is different than this electron, which has a down spin, even though they're both in the 1s orbital. Does that make sense? It's kind of technical, kind of specific, but I think we can think about that. All right, let's put another name on what we did here, and then we'll do some practice. All right, this concept right here, where we filled one electron in each box until we had to backfill. So right here, that is called Huns Rule. So let's title that. I made my paper crooked. Huns Rule. So we'll shorthand tell what that means. Fill each box with one electron until you need to double up. All right. Alright, let's do another example, and kind of talk about these Huns Rule and Pauli's exclusion principle before we get into practice, and then there's one more rule we got to talk about. Alright, so let's do sulfur. Okay. Sulfur. If we look at our periodic table, sulfur is number 16. It's in the P block. Okay. Sulfur sits at 3p4. 3p4. So when we write, it has 16 electrons. So when we write its electron configuration, we're going to go 1s2, 2s2, 2p. Do we need all 6 of them? Yeah, because that gives us 10 electrons. And then we go, do you remember? What comes after 2p? Go back to your notes if you don't remember. Yeah, 2p, 3s, and then 3p. So 3s2. Now we know that sulfur sits in 3p, which is the next one that we're going to fill in. And we said it's set in 3p4. Right? Yeah. So then when we draw our orbital configuration, an orbital does take up a little bit longer just because you have to draw all these boxes. but it is good when you are talking about, very specifically, about atoms and the way that they behave. So let's look at, let's put these two together, the Pauli's exclusion principle and the Huns rule. Huns rule says we're going to place one electron in each box and then continue to fill. So if we're working in 2p here, Huns rule says one fills each box and then we refill. Pauli's exclusion principle says that they have to have opposite spins. So when we go back and fill in 2p, we're going to make the arrow go the other way. And then we continue. Oh, making a box. Alright, so 3p has 3 boxes, so we're going to go Huns rule. 1, 2, 3. And then the 4th one comes back and fills in, going the other direction. Alright. Thumbs up if that makes sense. You got it. Easy peasy. Alright. Yes. I've never seen anyone do the boxes vertical. They always go horizontal that I've seen. I mean, don't know, but we usually go this way. That's a good question, though. Good clarifying question. All right, so the last rule we got to talk about today. If these things are spinning and they're flying around the outside of the nucleus anyways at this ridiculous speed, we said earlier that an electron could fly around the whole planet in 18 seconds. Ridiculous speed. How do we know where it is? How do we know how fast it is? We assume. There is some assumption in there, I guess. But that is what Heisenberg was very interested in. So Heisenberg he studied this and he came up with this uncertainty principle. So the uncertainty principle says that if you know the location of an electron, then you can't know its velocity or its speed. We'll just use speed for our purposes. Because if you find its location, then you have interrupted its travel, and it's so little that it can't keep going the same speed if you know where it is. Because if you shine a light on it or if you somehow stop it, you can't know its speed. It has changed speed. The opposite is also true. So if you know the speed of an electron, then you can't know the exact location. So once again, just kind of saying, we are thinking about all of these things and we know that they're true, but it's really hard to pinpoint those electrons. You would be able to like calculate it. Like we could think about if we see a race car and we know how fast it's going, we'll calculate where it could be in the next location. That's serious higher level math, though. So thinking about an electron, how little teeny tiny it is and how extremely fast it's going. by the time you calculated it, it would be in a completely different place. So it's a good question too. All right, so let's get to some practice. I'm going to stop recording because 20 minutes is